Hello. Let me make sure the stream is running. I turned down the microphone volume a little bit because I'm walking on the treadmill, and usually I tend to spike the microphone when I talk directly into the laptop, so hopefully this will get better. Yeah, I think it's working. Cool. Alright, so move this over. What was I even doing? We were working on visualizing AABB versus line, and today I just went further with it. I mean, I could just tuck it all inside of one loop. Here the only thing that I've changed is that now I'm generating all that data for the contact points, like the point that we use in the contact, the normal direction. We're now drawing a normal arrow, like the separation between the 2 points, and we're storing that contact. So I can show you. You can like zoom in. Let's go full screen, why not? Oh god, okay. So, see, we're still drawing everything, but now we draw lines for normals, the normal direction to resolve in, as well as if the endpoint is intersecting the AABB, then we draw a normal direction. But I don't like how it looks. You can zoom out. You see how it just kind of slides off? That's probably not what I want. So, well, like originally it would shoot out. So I was calculating like the original way I was doing it, like you saw last time. I was using T enter or T exit. Yeah, I'll just show you. I'll show you the last one too, just for full disclosure. I think we do LO minus T enter, VT enter, the vector for T enter. And the point is LO? Or is it VT enter? I don't know. I can't remember. And then we do like the inverse, so it's like VT enter minus LO. And then down here we do like VT exit. No, that's normal. This is VT exit. The vector for T exit minus VT exit. This is probably going to be all backwards, but just to show you, just to give you an idea of what I had set up. Like jumps. It's shooting it's pointing in the wrong direction, but you see that it jumps when the, as soon as the other edge takes over, it corrects. So I'm just saying that we're doing the wrong calculations. And right now what I'm doing, let me just go back to normal, please. Now I'm just taking the vector from the endpoint of the line to the center of the AABB, and that's also incorrect. So now we're just going to figure out, like, I want to point it in a cardinal direction for the AABB, so it'll either go up, down, left, right. There's no, like, diagonal vector that we're going to do. We're just going to pick one of the 4 cardinal directions, because I think that'll look the best. It's my own physics engine. I can do what I want with it. God damn it. So that's what we're going to do. We're going to do F... draw, rect, rotate. I can't remember any of the function names. Gonna do rect, rotate. Rect, rotate. There's a link to this Desmo stuff in the description, I think. So you can, yeah, you can just see. You can't make edits to it. You can probably copy it and make edits to it, but you can at least see what I'm doing as I go along, as I save updates to it. So we're gonna do B. This will just be the position. This will be 0, 0. We'll have B H extents, which will be 1 and 1. I'll add a rotation, but we're not going to worry about that for now. This will be 0. Just in case we want to scale this to an oriented bounding box later. So we have X, Y, C, the center of the box, dimensions, and the angle. Yeah, okay. Let me adjust this. I don't want to. I just want to plug in the half dimensions directly. So we're not going to divide them by 2 anymore. So this would be x, y, b, b extents, b angle. There we go. This is our box. So now we want to have a point. We'll just call it P. There we go. You see it? I don't know what this is. Oh, these are the extents. Let me get rid of that. Okay. So we have the box and we have the point. This line represents this point represents the end of the line. And so now we just want to determine where it falls in this AABB and which direction to resolve it. I think that's it. So we want to calculate the separation between this point and the surface of the box and the normal direction. So let's do b min x. Just call it min x or b min x, whatever. Equals the minimum of the x and the y, bx, by. Oh. I mean b dot x minus b extents dot x. I do oh yeah, okay. I'm doing this wrong. We're doing b dot x minus b extents dot x. For max x, we're going to add it to the y's. You know, you're familiar with this. B max y, B min y. So now let's do, is that all we need? Should I make a vector? Like the min corner? Yeah, b min. It's called b min equals. Am I doing anything? I keep like second guessing myself. Oh well. We can cut some corners since we already have a lot of the code set up, so we can take the separation. Let's just try to calculate the separation right away. And to do that, we need to like kind of project where the line is, where the point is on the AABB, right? So how do we do that? Let's just try, let's call it S for separation. Do like P dot X minus B min X, and P dot Y minus B min Y. And let's just see what happens. Oh. This is going to take a while. This is going to take a while of fumbling around. But that's how you learn. Why can't we see S anymore? Oh, I think it's directly on top of the point, yeah. Okay. Well, let's look at the code. At the position of the box, the endpoint LO and L1, they're just endpoints, so that's like the P and Desmos. And all we want is a cardinal direction, depending on the difference between the two. So I guess we can just start out with a normal. Yeah, let's just try to calculate the normal direction. That's what we want first. Let's do N for normal. And it can be one of 4 cardinal directions. And to figure that out, we want the difference between B pos. Let's just do diff equals b minus p. And then we'll take, like, we'll see if x is greater than y. In this case, we want p minus b. B minus p gives us the direction from b to p. So, yes. So that's the direction we want to resolve in. This is, if you see this, I can draw a little line. F draw a line from 0, 0 to diff. This line is the normal direction that we want to push the box in. So when the point is above the box, we want to push it down. When it's to the right of the box, we want to push the box to the left. If that makes any sense. So I don't know any tricks beyond just using a bunch of conditional logic, so we'll just use a bunch of conditional logic right now. Yeah, I've already been working on this for 2 hours beforehand, and I just haven't been streaming, so I figured I'll just start streaming now, and I'm kind of burnt out, but that's not an excuse. Gotta keep going. So, I guess we don't want to take the absolute value, so n equals, we'll just start brute forcing it. Let's just see if this works. So, the absolute value of diff dot x is greater than the absolute value of diff dot y. Turn 1, 0. And I guess we'll draw an arrow pointing in the direction that we want to resolve. So it'll be b. E plus n. Okay. So x is greater than y. What does that mean? Let's add another case to this piecewise function to get the normal direction. Let's say that y is greater than x. And then we'll do 1, 0 and just see what happens. The y value is greater than the x value for the difference. Okay. Oh, I see. I'm starting to understand. And to avoid an edge case, let's do like greater than or equals to. Just to stop that flickering. Okay. Okay, this is kind of better. Much better. Yes. Now we just need to change the direction if x is normal. Or if, what is difference down here? Okay, if difference is positive, then we want to do I wish you could split this into multiple different lines. If the x component, because what we're doing right now is we're just checking if the x component of the separation vector is greater than the y component. but then I would also want to flip it. So I guess we'll have two cases here. We'll put another little thing in here and we'll do if diff dot x is greater than 0. Okay. So if the x component is greater than the y component, we want to push in either positive or negative x. And the difference is on the right side. That will make it negative. And then we'll want to push in the positive direction. So if diff is less than that, okay. So now I'll add another case. We do that exact same thing, but now it's -1 when it's greater than or equal. Yes, okay. Look at that, isn't that wonderful? And then we'll just add all this same logic to the y component. This huge, unwieldy piecewise function. I guess I'll keep it like that. And then we'll do diff.y is less than 0. Yes. Copy this. Then we'll do diff.y is greater than or equal to 0, and then we'll do -1. Okay. I think that's it. That's the normal. So now we just want to find the separation between them. So if we zoom in, we will, I guess, project. Do we project? What do we do? We take. I need like a new case for this. Just call it like sep case. This is the separation case. So we're gonna have like 4 cases here, and we're just gonna reuse this piecewise function because that's all I can think of. We're gonna do 1, 2, 3, and 4. Oh my god. 1, 2, 3. Okay. So what's happening, you're going to have 4 different cases. So the separation, the point that we want to choose is on the right side. Right, left, up, down. 1, 2, 3, 4. Right, left, up, down. Those are the cases. That is, I don't know how to articulate this. Just bear with me. That is pretty cool. Do we get any flickering? I guess not. That's awesome. Okay, so the separation, the position that we want to pick, we're going to pick a point on the surface of the AABB. I'm sure we could do this much more efficiently, but this is all I can think of right now since this is the first time I've done it. And to save time Googling stuff or looking around, I think I can do it on my own. Blah, 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 blah. This is just cope. This is just cope for not knowing what the hell I'm doing. So we're going to do separation point, sep, equals, separation case is on the right, we're going to take B, we're going to give back a point that is B dot y, comma, B plus B max x, B dot x. 1. Not quite. Oh, I see. Plus b half extent x. B extent dot x. Yes. Okay. So you see this little pink point? That is the point that we want to compare against on the surface of the AABB. So we're just going to repeat this case for every other separation case. Separation case is on the 2, which is on the left. We're going to do minus. Then we're going to repeat this again for the up case. Separation case is 3. That means it's up. I'm going to do b dot x and then b dot y plus b half extents y. Please. And then one final case. I'm going to do b dot x minus b half extents y. Okay, so we should see a pink dot matching up with the direction of the vector. Yeah, cool, right? So now, I guess what we want to do for the separation, we already have the normal, we have the contact point. I guess this is the contact point. Like what happens when yeah. This is the point. We have the normal, and now we just want to calculate the separation, which is a scalar value. And so you just do the separation scalar value, sep. Depending on the case, it's just going to be the distance from the point to the surface in that closest direction. So I guess we can just repeat these things over here. Do like another piecewise function sep case. When it's 1, like this, we're going to take the distance between the x components, which will be the very edge, be b dot x plus b h extents dot x minus p dot x. Cool. And then we'll do that for every other point. 2 is go dot x minus h dot x. Yeah, that looks good. That looks good. This will be y. Separation case is 3. And then this will be separation case 4. Yeah. Okay. Cool. So I think this is everything we need now. We have the point, which I'm dragging, the normal direction to resolve in, and the separation amount. Let me just save that. And because this is an AABB, I just want to resolve it in one of the cardinal directions. So now we're going to port all this over. We're going to port this huge mess over. And we're going to figure out how to do all this stuff in C. And I guess just to show you. So where do we even start? I had this whole piecewise. Yeah, I had all this conditional logic in C. We'll just do that again. Who cares? And we'll do the absolute values, I guess. Diff.x greater than diff.y. Yeah, we'll need to do f_abs diff.x is greater than f_abs diff.y. Well, you calculate diff, vec2 diff equals b pos, the center of the box, minus the endpoint, right? just take that. If it's greater than or equal to, we don't want to have like a case where it's exactly in the center and then there's a degenerate normal. We don't want that. And I guess we can calculate all the cases in here. So we can get the correct normal to point in. Just comment this out. Just do vec2 normal equals that. Then we'll do diff.x is less than 0. 0 normal will be 1, 0. It's greater than or equal to 0. Make it point in -1. And I guess we can also do the separation here too, while we're at it. Do float separation. So this is case, like let's just match it up with the different cases that we have in Desmos. So x is greater than y, x is less than 0. We're going to have a normal of 1, 0. This will be separation case 1, which means that we're going to take this, where we do bpos.x minus plus, rb half extents.x minus lo.x. I think that should be right. Oh, and this is AABB. AABB. Am I doing this right? It's either going to get sucked in or it's going to get pushed out, and I guess we'll figure out which one that is when we start resolving it. But I think I might need to swap around the normals and everything else. I think this might just turn into a huge disaster, but we'll figure that out when we get there. Separation b.x minus half extents. Yeah, whatever. Let's just start plugging it in and see what happens. Difference.y is greater than 0. Difference.y is less than or equal to 0. We're going to do 1, 0. We're going to do y. Okay. Yeah. We'll do separation equals separation. Okay. Let's just plug in this whole mess to the other case where we're using L1. I can condense the code later once I... How do I say this? Once I see a pattern evolve, I can always condense the code later. So I'll just leave it very verbose, super clunky right now. Let's see what happens. So we should draw a line in the correct... Okay. So this kind of sucks it in. You can see the line that I'm drawing. I'm drawing too much text. Okay, so we want to point the normals in the opposite direction. Yes. Yes, it just works differently in my code. I'm drawing the normal from the contact point in the direction it's penetrating in the square. Whatever, you don't care. I'll just swap them around right now. Oh yeah, I also got these wrong. Of course. Let's see what this looks like. Okay, so it's pointing up in that case. It's pointing out. It's pointing down. That's nice. Okay. Okay, I think this should work. Hey, look at that. Cool. Hey, that's awesome. That's exactly what we wanted. That's awesome. It's not sliding off anymore. It shoots up. That's so cool. That's exactly what we wanted. Wowee. Look at that. What happens in that case? Awesome. Okay. I think this is working. Yeah. That's cool. Okay, yeah, it'll just sit right there. That's fine. Oh yeah, I also made it so I can slide these around. Slide the dots around on the static geometry. You can like bend these. Bye bye. Cool. There it goes. Can we catch it? Can we catch it in time? Yeah, cool. This is ridiculous. Cool. Isn't that weird? Okay, so I think AABB versus line is finished. We can have it sliding around. It's not rotating because it's axis aligned, but it looks pretty good to me. So, what do we do next? We won't have like any really tiny degenerate point cases. So I guess what we should do next is I guess we should set it up for OBBs. Like, do I really want OBBs, or is that just a huge waste of time? Because then we need to start dealing with rotations, and I can show you. Let me save this. This is kind of backwards, but I don't want to fix it. I don't want to fix it for you. It'll depend. The normal direction that you have, it'll depend on how you calculate, how you want to separate the entities, like the order. Like if you have entity A versus entity B, and then the normal that you want to separate them in, that's going to depend on your exact architecture. But here, I'll label these things for you. So we'll have box, and we will have point. This is an AABB versus point, right? There you go. This is the... Do we even want to draw this? I guess we can. We can draw like the normal. What did I do wrong? Oh. Okay, we can't label that. Can I? Okay. Yeah. That's the normal that you would want to result in. Okay. Yeah, so just for my convention, I'll swap these around for you after all. So we'll do -1, -1, -1, 1. Yeah, okay. And now we're drawing where the box is going to push itself. And then I'll correct the separations too. I guess my separations are technically backwards, but does it make a difference? I guess it doesn't make a difference. Separation. Yeah, it doesn't make a difference. Okay, you can see the separations. Oh, the cases here, they're backwards. Maybe I should look at that. Maybe it'll get sucked up if we okay, good. It is not, in fact, getting sucked up. Only when the endpoint is on the other side. Okay. I guess we can always debug it later when run into actual issues. But I will fix this. Separation. Because we want the separation to be negative when they actually are interpenetrating. So this will be separation case 3, b dot y plus half extents minus p dot y. Isn't that what we want? Oh. No, I have it backwards. From the top of the box, we're going to subtract that from p dot y. P dot y minus. Oh. That's also wrong. Okay, there we go. Got to wrap it in parentheses. And then the bottom case. Okay. That also works. So let me just step into this in a little demo really fast just to make sure it works. So we're going to calculate the separation when we're in endpoint L1. Difference is less than 0. The difference in that case is it's pointing down. The box is right here. The point is right here. The difference between them, box minus point? That'd be pointing. Yeah. So when you subtract something, you're going from that something you subtract to that the direction of what you're subtracting from. So yes, it's going to be negative. We're pointing down. That's the direction that we want to resolve the AAB in. We're going to do L1. So this is going to be positive, actually. The separation is going to be positive. Yeah. So we want to do L1.y minus. We do this. And I think this is going to be the case for one of the x directions too. We want to do the same thing over here. LO.y minus, and wrap this in parentheses. Oh God, what did I do? Okay. It's going to be one of these cases where, yes. Can compile it. I think it's the first X case. Just trying to catch all the weird edge cases I programmed into this. I think it's this case. It's going to be an L1. Yes. So separation is going to be positive here. Yes. So once again, we want to do L1.x minus and wrap these in parentheses. The right one, L1.x minus. Be LO.x minus. Okay. I think we'll have the same problem in Desmos. Yeah. So for the first case, we want to do P.x minus this stuff and then wrap it in parentheses. There you go. Just so that we make sure separation is negative in every case. And the normal is we're drawing the direction that we want to push the box in. So I guess I can draw an arrow actually showing the vector that we want to draw. F draw arrow, X, Y, B, B plus N. There you go. So it looks ridiculous, but that is the arrow showing the normal, that the direction that we're going to push the box out of this penetration, because we're treating the point as static. So the box is the only one that's going to move. So there's a lot of assumptions about this. But there you go. There you go. That's all we're going to worry about. So, yeah, huge mess, very verbose, but oh yeah, I need to test it now. Okay. Looks like it works. I'm gonna say that it still works. That's so cool. What happens if we like press it in? Oh, that's awesome. Okay, cool. It doesn't get stuck. That's awesome. Okay. I keep saying okay. Oh, great. It's awesome. Cool. Great. What do we want to do next? So we're at a crossroads where I can either scale this up to an oriented bounding box, which means that I would need to get the separation axis theorem working in my engine, which would be a nice long-term goal, because then I could support fully rotating. I really want that. I really do think that would be cool. And I already have the separating axis theorem working in Desmos. But to remember how, like I did it a month ago, I can probably pull it up in Desmos right now. Go to graphing calculator. Go to dark mode. Yeah, separating axis theorem right here. So it's like 160 lines, but you know, when we have a collision, I highlight the whole area and then I draw the points that are interpenetrating, because in 2 dimensions you can have 2 contact points. I don't have the normal directions, but you know, I could spend another day. I think this would only take a day or 2 more to get OBB, separating axis theorem, so I think I will. We're gonna see what happens, and we're gonna try and scale up the AABB V line to an OBB V line. And so to do that, I think I also demonstrated this little step. OBB V line. I showed. It's one of these. I named them all the same thing. OBB V half space. Yeah. Okay. So we'll move this box around. And so right now, like around the origin, I'm drawing the box in its local space. And so what happens is that when we rotate it, when we have an oriented bounding box, we inverse rotate everything relative to it. So this line up here, when we compare it to the local space of the box doesn't change. The box is still an axis-aligned bounding box, but the line's orientation changes. So what we're going to do is, I guess we're going to keep that function, and now we're just going to add an edge case, or just modify it so that we check the type. So we can either send it an AABB or an OOBB. And if we send it in an OOBB, then we're going to transform all the points from world space to local space, where it becomes an AABB, transform all the line points to its local space, and then do all those same comparisons, and then whatever results we get, we rotate them back relative to the oriented bounding box. So I guess we're going to do a lot more debugging. I might as well just, instead of trying to fit it all into that one function, this is going to be so stupid. But we are going to just copy it. We're just going to copy all this code. It's going to be a huge mess. We're going to make another function for AABB versus line static resolution. Another assumption that I should let you know is that we're assuming that all the lines are static. Like if we have a line, like lines that can move around in the engine, then if they're like perfectly parallel, they're infinitely thin, so they'll just pass right through each other. Like we can add the slightest velocity and there will be no detection of penetration. Like even if it like intersects at an angle, it'll slowly fall flat and then it can just phase through. You see what I mean? So we're not going to have any dynamic lines in the engine. We're only going to have circles, capsules, and bounding boxes, like rectangles, and that's it. Other shapes, like hexagons and stuff that I want to add later, if I want to learn GJK, or if I want to expand the separating axis theorem to handle more than 2 axes per shape, then I can do that, but that'll take way longer than I want to commit. So we're going to do OBB versus static line. Make sure it compiles. Oh yeah, I can tear that out. Tear out this little, oh my god, I wrote so much code. This is when I was, earlier this morning, I was like, oh yeah, okay, I'll scale up this function to also handle OBBs. But you know what? We're not going to do that anymore. We're just going to make a brand new function. We're just going to assume that we're passing in an oriented bounding box, and we'll call it OBBRB. Just going to change every instance of AABBRB to an OBBRB. AABBRB. Okay. That should still work. That's great. And we basically have everything that we need in this function. Now we just need to rotate all the points around. So I also need to plug this in. So we're going to do AABB V line. Oh, and we're still like in that area. Static resolution. Let's do OBB. Case OBB. OBB V line static resolution. And this is in the physics collision inspector, but we're also going to plug it into the impulse thing. Physics impulse update. Right down here. We compare against all the static geometry. And now we're going to add in no circles, no capsules, no AABB. We're going to enable an OBB now. OBB entity. Yeah, I think you can see it this whole time. I was actually drawing it. Yeah. So this is an oriented bounding box. And I also added in some code earlier where I can rotate it by dragging a point. Only like the top left or the bottom only the top right or the bottom left point. Like the other two corners, they don't work just because I wanted it to. I just duplicated the capsule code, and the capsule only has 2 endpoints you can drag, so, you know, if I want to add more code, I could, but it doesn't really matter, like, oh, we can't drag this end. Huh. Okay. I don't think I'm getting the rotation right. I don't think I'm calculating. Oh, yeah, okay. So this is a consequence of rotating it. In the code, rotate. Okay. So I guess we don't draw the correct angle? Or we don't update it when, how do we calculate? This isn't really a big deal. Is it? Does anyone care? Nobody cares. But when we rotate the OBB, I guess I don't give it the correct orientation. How do we do that? We update the angle. But do I just do it wrong? We're still drawing it correctly. Just gonna debug this now. You can see that when I go to drag it, oh. Yeah, it is highlighting. That's so weird. We're drawing it with the correct angle, but then we go to drag it. I think my dragging code is wrong. Oh, yeah. I want to reverse rotate it. I think I want to reverse rotate it. So we're going to do minus sine R here. And plus here. And now it should work fine. Yes, okay. That was just a little, I guess I never tested it thoroughly when I originally wrote that code. Because, like, for any, like, you're treating it as just a pixel buffer for any XY coordinate. It's going to land in this oriented bounding box, but you want to transform it back to its original position to see where that point would actually end up inside the oriented bounding box. So you don't rotate it. I was rotating it again. You want to inverse rotate it. And you do that by, instead of doing, like, minus sine R for the X position, for the X component, you do negative sine for the Y component, if that makes any sense. You can look up the two-dimensional matrix rotation and then the transpose of that, but we're doing the transpose of the rotation matrix. That's what that means. So that's nice that we got that working, another bug fixed. But that's not what we were here for. We are here to, okay, cool. So you can see that we have all that code set up, but it's treating the oriented bounding box as if it's an axis aligned bounding box. You see how we're like drawing where all the corners are, or where we think they would be if this were an axis aligned bounding box, but it isn't. And so now we just want to rotate all those points. And that's what we will start doing. OBBV line. So B min, B max. We'll do this after we, this is the first confusing thing, so we do need B min and B max. Yes, okay. We don't need to worry about that, but we need to calculate the vertices differently. The vertices will now be, you want to rotate it. We want to rotate the extents, so we'll do like vec2 rotated vert 0, right? That'll be vec2 rotate, my little rotation function. Or do we want to inverse rotate it? No. So we're starting as if it's an axis aligned bounding box, right? And we're picking all these vertices, but we want to rotate it to get where the vertices are. Or do we want to do this, or do we just want to rotate everything relative to... This is so confusing. I think we need two sets now. We want, like, the regular set, B verts, and then we want rotated verts. So we're going to do BR verts, box rotated verts. We're going to keep all this original set the same. And now we're going to do OBBRB angle. That's how we're going to rotate it. And we're going to feed in a vector, which will be BH extents. And depending on the vertex, like we're going to make some of them negative, some of them positive. 0, 1, 2, 3, 0, minus x, plus x, plus x, minus x. And then this will be minus y, plus y, plus y. Just make sure that compiles. EC2. Okay, that works. And so now I'm going to take bpos plus RV 0, 1, 2, 3. Yeah, okay, perfect. So we have the regular, where they would be in local space if we don't rotate them, and then where they actually are when we rotate them. And for the line, all the line positions, I guess we'll do the same thing. So what we need to do for the line, I'm going to show you in Desmos, wherever Desmos is. I have so many different tabs open. Close out of that. Okay. I think this is it. Okay. Yeah. So, where was I? So, it can be anywhere in space. And we want to... Let me just zoom in on this. The line can be anywhere in space relative to the oriented bounding box. But in order to put it into local space, we need to subtract those points on the line with the relative position of the bounding box. So you can see that as we move the box further away, the line moves further away in the local case. You see that? So first we need to subtract the position. So we do like L1 or L0, the vertex of the line, minus the center of the box. And that'll give us its position relative to the origin. And then we rotate that. And then we shift it back by adding the position of the box again. If that makes remotely any sense to you. So that's what we're going to do right here. We're going to do AABB, like let's just do it to all of them. Actually, why not let's just duplicate all of this. We might need the original positions, and we'll just do rotated verts. So, or like centered verts, or like let's just do LR verts. And so this will be like AR, A rotated, LAB rotated, the center rotated, and scaled and repositioned. Let's just rename all of this stuff. It's hugely messy, but whatever. Vec2 rotate minus OBBRB, or like bpos. So we're taking the world space positions of the line and the box, and we're subtracting them, so we're moving A relative to the origin. And then we're rotating it. Am I thinking about this right? I think I am. How do I do it in Desmos? Oh god. L rotated. Yeah. So we're just treating them, we're keeping them like around the origin, but I guess we'll add back the OBB case, because I don't think we treat anything as if it's at the origin in this code. It would make things maybe a bit cheaper. I don't know. Whatever. Yeah, so we're going to add back. We subtract OBB1 here, but in the code we're going to add it back to the end. BRB angle. And then plus B pause. Yeah, and that compiles. I think that is what we're going to want to do. B. It's going to be B. Yeah, and then LAB rotated is going to be that. Center rotated is going to be that. This is the projection of B verts minus LOR. BVO to LR. Yes. Okay. As if it's now we're comparing the unrotated, the AABB points to the rotated line. So the rotated line is now what's going to be in the AABB space. Oh, I forgot semicolons. Can that compile, please? Yes. So, L verts and L rotated verts. That is going to be AR and VR. I don't even know if we use those. And then all these positions to the screen, let's do, let's rotate them all too. BP, well, that doesn't rotate. BV, R? B verts, God. BR verts. So now we're gonna have BR. Box rotated vert 1 to the screen. It's going to be BR verts. BP screen. We don't need to duplicate that again. LO screen. Let's duplicate all these and then feed in the rotated positions just to make sure that we're drawing everything's right still. Line OR screen. LCR screen. LOR, LOR, line center R. Yeah. So we're going to draw circles at the endpoints of the line. That's fine. Okay. I think all that's fine. And now we get to how to project. So now we're going to take BV0 to L. 0 to L. Calculate these earlier. Yes. BV0 to line rotated. Going to compare all these to the rotated line, and then we're going to make these the rotated lines. LAB R2. Remember, I'm just adding the R to denote that these are the rotated. These are now in AABB space. And now we're gonna LABR, LOR. We're gonna slab test. Or we still have the Bmin, the Bmax. Now we're going to set these to LOR and LABR. T enter and T exit don't need to change. Intersection, none. Make all the line stuff relative to as if it were rotated. I'm probably going to miss something here. I don't think the line normal has to change. These are the half space tests where we take the vertices of the AABB relative to the line rotated to the AABB. Change this type to OBB line. Oops. Contact OBB line. Do we not have that? Okay, we don't have that. OB line, OB line. I had it like, oh yeah, I'm gonna add GJK. I don't think I'm gonna add GJK anymore. That's just too much work, and we don't need it. And now I need to add that case down here too. Line. Okay. So, if the vertex is within the line, VVO proj, we're going to draw a circle at the RVO screen. And before I change anything else, I'm just going to draw it the RVO screen, the RV1 screen, the RV2 screen, and the RV3 screen. Okay. It's not right. Okay, so in some cases, we're drawing some of the lines right. Yes. We just have the half space mixed up. So the center is on this side of the line, but you know, when they penetrate, you see, oh, we're drawing the wrong corners. So we got to fix that, but I need to take a piss. Be right back. Should I pause the stream? Oh well. It doesn't matter. I'll be right back, people. Getting there. Where was I? Lose all the contacts as soon as I step away. Is the stream still up? Yep, there I am. Okay. Start at the treadmill. So we were drawing the half-spaced stuff wrong. I wonder how much work we have left. Okay. So if the half-space is less than 0, BVO projection is greater than 0. These are the vertices as if they're in AABB space, minus the rotated position of the line. LABR. Am I missing something here? Depending on the half space that the position is from, I don't think that should change. I'm drawing a lot of overlapping data, so we're going to start commenting out all those other lines again. So, static geometry, going to comment out all the walls. We'll just see what happens. Well, it's definitely not right. Oh, I think I'm just when the box rotates. Oh, I think I need to inverse rotate everything. I was just rotating it, but I actually want to inverse rotate it. Inverse rotate the line. Okay, simple mistake. Just make sure these are all the rotations. Yeah. We only have a little set of rotations, and we want to forward rotate, like we start with the AABB. We want to forward rotate where the vertices will end up. And then for the line, relative to the already rotated oriented bounding box, we want to inverse rotate them. Or like from your perspective, this is rotation. Like we start going positive theta around the unit circle. So we rotate the box, and then we have like a line right here relative to the rotated box. We want to inverse rotate it. So we're going to do vec 2 inverse rotate. This? Yeah. So that should get us closer. Yes. Okay. This is good. This is very good. Yes. Okay, I think the corners are correct now. So now we just need to draw the corrected contact points, all that other stuff. But the vertex half space checks are correct, and that's like half the battle already. So the point, the contact point, is the position of the rotated vert. BR vert's 0. Let's do all this. BR vert's 3. The normal is going to be from the projection onto the line. And I guess we could just start computing it in regular space. So we're going to do like the rotated vertex minus the projection onto. Do we need to forward rotate these back? Oh boy. This is where I'm going to start get confused. B1 to LOR. Let's just make another whole set of these. Why not? BVO to L. Oh, I think I overlooked these. No, I did. Okay. Do I reuse this anywhere? BV1 to L. Do I reuse that? I don't. Okay. I'm getting confused and distracted. Let's just look at the first case. So, vertex 0, we have the box. Vertex 0 is right here. It's interpenetrating the line. The normal between them is we're gonna project it back onto the line in world space. Yes. B rotated vertex O projected onto the line. I don't think we have that. B rotated vertex BR is going to be the rotated vertices projected onto the regular line, world space line. And we're going to do all this again. These aren't rotated. Rotated vert projection. We're going to do BRVO. Yeah, I know, this is going to get confusing. So this is the projection from the rotated vertex to that line in world space. I'm going to call this B rotated vertex to the line projection. LO plus BRVO proj. Right? So instead of BVOL proj, yes. Okay, so these all become R. Getting closer. Now we're just calculating, like, I know I'm mixing up all the coordinate spaces, but instead of just rotating everything back, I'm just going to calculate where everything is up front, and if it gets too expensive, I can always optimize it later. Once we have the working code, this is all I care about. I don't care if it's slop. I don't care. As long as we can hit 60 frames per second, that's all that matters. So we have the normal between the projected point on the line in world space and the rotated vertex. Change all this. The point becomes the rotated vertex. That normal looks correct. And then we're just going to swap those. So instead of doing like the projected point on the line minus the rotated vertex, to get the separation between them, to make it negative, we're going to take the rotated vertex minus the projection onto the line times that normal that we got. Let me draw the arrow from, let's make all these the rotated vertices. That's the arrow. The circle should be correct. I'm probably missing something somewhere. Draw a circle. BRV1 screen. That should be correct, should it not? Okay. Let's just see what it looks like now. Okay. Okay. Doing something wrong there. Oh yeah, okay. So now we need to worry about the endpoints. Just make sure we have these right. Yeah. Okay. I really do think that should work. But now when we intersect these, like we're intersecting the far side, and then we're drawing the wrong entry points, and then yeah. So the penetration. Do we even use these? Yes. I'm going to take the rotated point. With the rotated point relative to the b min y, b min x. Because I think these are in world space. Yes. Yes, we're rotating. When we denote it as rotated, that means we've rotated it and shifted it into the world space as if it was aligned with the AABB of the OBB. I'm getting burnt out. I wanted to go for like 5 or 6 hours, but I got sidetracked and spent 2 of those hours programming without streaming. There's always tomorrow. Just gonna procrastinate. LO screen. Let's do LOR screen. L exit. T enter, T exit. I think these are going to be different. Are they? So when we do enter and exit, those are relative to... We're going to need to rotate these. We're going to need to forward rotate these. So this is called vec2 v t enter forward rotated equals vec2 rotate v t enter OBBRB angle. Then we'll do the same thing for exit. VT exit forward rotated. This is very stupid, I know. Just trying to get it done as quickly as possible. Well, no, this is like the only way I know to do it. So, apologies. And so, we're drawing the point on the line. So LO screen rotated, is that? I don't think we want that. We're drawing, yeah, we just want to, and forward rotated. Exit to screen. Yeah, okay. Gonna convert these to screen coordinates. T enter forward rotated, T exit forward rotated. This is disgusting. T exit forward rotated to screen. Let's just see if we can get that right. And then L1 forward rotated to screen. Let's see if we can at least start drawing those correctly. T exit FR. T exit FR screen. T exit. Oh, SFR screen. Oh, I see. Little typo. Okay. We're getting there. Okay. Still definitely wrong. What did I do? Okay. Still wrong. Look at that. This collision inspector thing is like right where I want to test everything. I guess we can keep this running and I can just change the points. I can just hot reload it. So this is the case where we are looking at L1, the endpoint of the line, and it's penetrating. And we have this little red point right here, right? This red point should instead be on the line right there. So L1 is penetrating. L1R. Just make sure these are what I expect them to be. Yes, that's all still in world space. And we're drawing circles on the L1 position of the screen, then the entry position. Okay, so the entry position is wrong. Draw arrow, yeah. T enter FR screen is incorrect, I think. Oh, that's because we want to subtract OBB and add it again. I think that's it. Minus OBBRB. Well, you just do minus B pause plus B pause. And that should fix where it is on the line. Yes, so now you see I mean, it's kind of hard to see because the line is overlapping it. But now, when we're intersecting the line, we now draw. I mean, I don't even think that matters because we don't even. If we're intersecting the endpoint, we don't even care about the slab test. We just want to point in the direction that that point is, like we did earlier. But at least it's drawing correctly. I think everything is being drawn to the correct position now, so that's good. We're getting very close. Difference between center of the box and the rotated position. Yeah, we'll do LOR. Make it relative to the box. The AABB. And then we'll do the same for this. I just want to test. I'm going to set a breakpoint right there because when we're intersecting with L1, we draw an arrow for. Okay, so I guess we're just drawing it to the wrong position. Draw arrow. LO. Why do we do that? Is that a typo? I think that's a typo. I guess I just never noticed it last time. Draw arrow. Point normal separation contact count. Yeah, okay. That is just a typo. Okay. This is the last step. We're taking the difference between the bounding box and the line rotated relative to that axis line bounding box. I think all the normals are going to be the same, but instead we're going to have to rotate them. So we're going to forward rotate them. Back to rotate OBVRB angle. And let me just check that that compiles. Yeah. I know this is stupid. Just going to leave that code in just in case we're wrong. -1, 0, 0, 1. And I think we're going to have to do the same thing here. 0, 1, 0, -1, 1, 0. And -1, 0. It's a lot of work just to get a collision between an OBB and... I mean, it's not that much. We already did all the hard work. Now we're just translating, rotating everything back. So now we're rotating the vector. And now the separation. We do L1R. Yeah. That'll give us the correct separation. L1R. L1R, L1R, L1R. And we'll do the same up here, LOR, LOR, LOR. Yeah. This should be correct. I think. Just run it to make sure that everything is being drawn correctly. Yes. Okay. Oh no, it didn't work. Oh no, okay. That's because I didn't have walls there. I need walls. I was like, oh no, it slid through the wall, but I forgot I disabled that wall. Static geometry, let's re-enable all the static geometry, which is just lines. I just put them all into an arena. Let's see. It works basically the same as an axis line bounding box. Let's rotate it. Yeah, that's cool, right? Cool. So now, all we got to do... God, isn't that cool? That's so cool. So now we just need to... It's not rotating because it has an infinite inverse moment of inertia. So now we just need to add a moment of inertia to the OBB. We do that. Entity... That's so cool. We already have all the code for OBB versus line. That's really not that bad. We did that in like, when did we start? I don't know. I'll look at the stream later, but couldn't have been that long. No, I've been doing that for like the past half hour at least. Yeah, it's been a while, I think. I'm just playing back through the stream, but I mean, at least it works. I didn't know if I could get it to work in code, but my mental model turns out to be correct. So that's very reassuring. Anyway, enough patting ourselves on the back. We still got to add the moment of inertia. So we do it here. We have the mass. What else do we have? We have the I and then the inverse I. We have the mass. We have the inverse mass. Let's do the I and then the inverse I. I don't know the equation for rectangle's moment of inertia. Inverse I is over RB I. Let's just make sure that compiles. Okay, so now we're going to Google 2D rectangle moment. Mistyping everything. 2D rectangle moment of inertia. It's just, well, here we go. We have some AI slop. X and Y is cubed divided by 12. Well, we can just make it 1 over 12 for right now. Let's do 1 over 12 and see what happens. Hey, look at that. Crazy. Okay. Wow. Cool. Okay, so the moment of inertia definitely doesn't look right because of how it jiggles, but that's crazy. I mean, it has infinite friction, so we can add that too. Let's like make the friction 0.5F, and let's we only initialize the entities once. Huh. Okay. That's strange. It's getting pushed out. That's crazy. Okay, so this isn't right because the OBB is falling into that line. Oh, that sucks. Let's see what happens. Yeah, and it's the same thing on this case. Okay, so the endpoints aren't quite right. Huh. That's freaky. We have like a perpetual motion device. Yes. Okay. It doesn't know. I think we have another edge case here where it'll start penetrating the line, but because the line, it's like it's right here relative to the box, it's getting pushed in, and so then it just knows to push in this direction. So that's another edge case I need to think about. Damn, we're so close. Okay, that's weird. Oh yeah, we have this whole playback system. Snapshot playback. Okay, let's see what happens. Okay. I, in the playback system, we generate the contacts every single frame. There we go. Interesting. Okay. Yeah. I'm trying to think. Huh. Only when it's like a really slight incline. What? It's not happening anymore. Does it depend on the... It's weird. I think there's a typo somewhere in my code. No? Okay. So it's still getting caught there. What if we rotate it? Like that. Okay. Let's try to rotate it again. Let's check every single edge. Huh. Okay, so it is getting caught there. Sometimes it does get caught. Ah, this was bizarre. I guess I didn't see this as a problem with the AABB because I guess it just doesn't trigger this case because it doesn't slide along the line. It's crazy. This is cool though. Like I have, it's kind of working, except for when it gets caught on lined endpoints. But I don't really think I'm not even gonna have. This is just for capsules, really, because a line is just a flattened capsule, and really I'm only going to have oriented bounding box bouncing off other OBBs or capsules or circles. So this line case is just for early testing. But I do want to figure out why it's wrong. But I have no idea where to start. Like, test again. Make sure that it happens for every single edge, so I'm not crazy. Yep. Yeah, the box only knows to resist. Oh, why is it falling in like that? Freaky. If I just stare blankly at the screen for the next hour, maybe I'll get an idea, because I'm drawing blanks right now. Too bad that I zoom in, we start chugging. What if I just stop drawing so much stuff? Move all that off screen. Oh, we're still chugging. What's the difference vector right there? I think it has to do with the way that the rotated box is interacting with that line, because it should just point out. It should just point straight up. No, because it's falling in. It's falling into it, so we're hitting like the X condition. I can just step into the debugger. I forgot about that. So we're hitting LO. We're penetrating LO. Is this in the OOBB? OBB. This is the OBB function. Static resolution. Oh. Okay, here we go. So, we can just recreate this exact case in Desmos. Let's just do that. Let's do that right now. God. Where'd my mouse go? Oh, yeah. Okay. Then Desmos over here. Let's just make a test, little test case. Should we preserve this? No, let's just make a new thing. Let's make a new graph. Get rid of all this other shit. Okay. This is what we want to do. Okay. So we're also going to need to port over that code to calculate the penetration in the normal direction. Okay, let's copy over those positions. So here's the position of the box. Here is the OBBRB angle. Let's set all that up. Let's allow the rotation of the box to go to -2 pi. Yeah, and so now it'll be -1.44636. Okay. Position will be 2.1. Okay, and then the line positions. Let's just look up LO and LR. Okay. Okay. I would like that snapshot thing too, because I don't even know if we should get this far into the line. Whatever. So we have the correct orientation of the box, the position of the line. Let's make sure that it's reflected. Okay, so this is what it looks like in when the line is in the oriented bounding box space. So we're penetrating this line right here. Let me open up that other thing and we'll like copy over that code. We will do the normal direction. Yeah, okay, so we'll take the difference and this will be between the box and the point. Box and the rotated point. Diff equals AABB1 minus, let's just do LO. LO rotated. LO rotated. Centered? Yeah, okay. So this is where that point is, or where we want to push the box out of this. Just draw a line. Draw a line. Diff 0, 0, T. Oh. That's LO, so we are colliding with LO. Center minus the rotated point. Point in this direction. Oh. Do I have it backwards? Just like label LO rotated. Ah, okay. It's actually right here. It was right here this whole time. I was looking at the wrong thing. So from that point, we want to push it in this direction. Okay. I've burnt a whole lot of time just staring blankly and it was correct. So stop drawing that. We have the difference. Let's take the normal now. Oh god, what did I do? Let's take the normal. And this will point in Y, positive Y. We want to push it out. Is that correct? Do we actually want to push it in that direction? I guess so. Shit. What happens if we move it like right here? I want to push it in the negative X direction. Shit. I think that's correct. We need to somehow change the direction that we push in based on. We can't just keep the same logic from the AABB. We need to invent something new for the OBB, I think. Reset the angle. It's going to push it up. It's going to push it down. It's going to push it to the right when it interpenetrates. Yeah. Okay, so that is correct then. So it's a consequence of the logic that we programmed in. It's working as intended. This is not a bug. The logic is working exactly as we intended it. Man. It's not really a big deal. Like, we're not going to... I don't think we're going to intersect lines in the actual engine ever. This is just for the initial testing. But I still want to figure it out. Set it back to normal where it was. Yeah. That sucks. That really sucks. The y value is slightly greater than the x value, so we're going to push it up. And somehow that keeps the box balanced. Let's try this instead. Just one last thing. I don't want to stare blankly at the camera forever. So instead, what we're going to do, we're going to change the logic, and we're going to point for the normal. We're going to point from the center of the box to wherever the line is interpenetrating. And then we'll need to calculate the separation again in that direction. So we'll have the center of the box, the point. The box will point. It'll like just point off in whatever direction the line is pointing. That'll be the normal. And now we just need to determine the separation between them. Oh man. And so the separation will be the normal direction times the half extent. We want the separation value to be roughly correct. So let's do, instead, let's just do OBB1 minus LO rotated centered. Okay. So that's the normal that we want to push the box in. And then we need to calculate the separation along that normal from... Man, I just can't figure it out. Let's just call it normal. Normal normalized. Normal and normal normalized equals F normalized. Normal. That's where we want to point. That's the direction we want to point in. What happens if we multiply it by the extents, like OBB, OB extents? Where do I have O extents? I can't make sense of that. We're just trying to calculate the separation between the point and then wherever that would get projected on the box. I mean, we could just calculate the lines for every box, then figure out where that point would land, but I feel like there's a simpler way of doing this, and I can't quite wrap my head around it. And I'm burning tons and tons of time. So I think to save time, well, no, because then I would need to compare the projections onto all four lines of the box. This is tricky. I could just cast that line all the way to the corner of the box, but how do I figure out where that surface point of the box is? There's something very simple I'm forgetting here. I want to make sure the separation is right, otherwise, maybe you could explode in the simulation. We want to get the surface point let's try this. We'll do OBB1 centered plus normal, and we'll just try to determine where that is. Surface. Okay. Where is L1? That's not right. Hello, rotated. Let's just normalize it. Okay. So based on that, we want to somehow determine, we have this vector, we want to extend it all the way to the surface of the box. And there's probably a way to do this, but my grasp of geometry is still very poor. It turns out. What a shocker. Guess we could clamp it. What if we multiply it by 2? This is so stupid. Okay, so just surface point. Let's just call this surface. Surf. We'll call it surf, right? Okay. And so now what we'll do is do surf clamped. Surf C. And we'll clamp it to the minimum X and Y. Yes. Yes. Can we clamp? Can we do min? Oh, this is so stupid. God. We're going to clamp it to the minimum X and the maximum Y. But I don't know how to draw a point like that. Whatever. Wasting too much time. I'll figure this out later. Sorry, ladies and gentlemen, I just could not do it. We'll just hard code the separation to 1.5. I don't know. Point is all that. You have the normal, we have the point, we have the separation. Okay, let's just see what happens. Okay. Absolutely terrible. It kind of works. It kind of works. Okay. Not really. It does not work. Okay. Yeah. Okay. How'll that work? I'm like, no, we can make this work. No, we can't make it work because it'll still point it back in towards the line. So we need to totally rethink this approach. I'm looking at the replay where it does that flip. Let's do it again. That's silly. Oh well. Yeah. Okay, so it's still totally broken. Gonna need to think of some new way to solve this problem. But I've just been staring blankly at the screen for too long. I'm gonna make some dinner and I'll think about it some more. But thanks for tuning in. We made some more progress. We got the AABB versus the line working, but it falls apart when we start rotating the box, and I need to figure out how we can figure out that whole endpoint problem. And I think we might be able to do something with the slab test. But I'll experiment with that in Desmos. It's going to take like a day of just reconstructing all the geometry that I forget. Like every time I go to sleep, I forget everything, and then I have to relearn it in the morning until it truly becomes locked in, and I'm not there yet. So anyway, thanks for watching. I'll see you later.